Okay, so after a long journey from basics of the DSP theory and going to the random signals and now you're coming to multiple sensors. So if we have multiple sensors, do we have any gains out of that or not? There are so many applications related to the multiple sensor case. I am talking about the microphone array, but it doesn't necessarily mean that it just works for the microphones. It's also working for the radar case. So whatever I say here today almost completely would be applicable in the case of radar tracking or radar systems, telecommunication systems. And in many other cases, whenever we have some sensors, so multiple sensors, that we can get the data out of that. So in wireless communication or in the radar case or in multiple microphones, any number of the sensors that we have, and then we have some number of the sources, then we can apply the theory that we talked today, but I specified the talk today to the microphones because they are more tangible and we have a lot of examples to do that. And if I can finish the lecture slides in the morning class, then in the afternoon we'll try to do MATLAB examples. So topics that we will encounter and you will see in the literature, they are mostly with these keywords of microphone array, localization, and beamforming, and we're going to talk about these concepts in this lecture today. So the beamforming or spatial filtering, so that's another name that we may encounter. There are a lot of applications for the microphone arrays, and the same way we can find the same applications for the radar. So microphones are sensors. They can record the acoustic signal, and the same thing happens for the antenna. So when you have antenna, it means that there are sensors that are grabbing, actually recording the electromagnetic signals, so the waves, and the same for the radars or wireless systems and so on. When you have multiple sensors like the microphones, then they are used actually in many cases like the robotics. So you have a robot. Here you see that humanoid robot. If you deploy some microphones in the head or in some specific place on top of this robot, then the robot will actually be able to localize the source. So if you want to give the robot a command, then if a number of the people are in the room and robot is actually is supposed to localize a specific person and then to give a response to that person, so first of all the robot should localize that person and then to get the information, the command information from that person. In order to do that, just the same as what people do using 2 ears, the robot can listen to the entire acoustic signals grabbing in that environment and then tries to localize toward the person which is actually interested. So we have also another example like the speech control case, that a series of the microphones is called an array, and this array is deployed inside the car, and the car is actually is driving fast, and we know that inside the car there are a lot of noises from the environment, specifically when the window is open. So all these noises somehow deteriorate the quality of the voice that can be communicated inside the car. So if we can find kind of solution for this kind of problem, then that would be so nice. And we can communicate inside the car much easier without that much effort. Normally you see that inside the car people are shouting, and they are actually dissipating a lot of energy in order to communicate. Because of the noise, they have to make a lot of SNR, and that needs actually spending a lot of energy out of that. So if we can deploy microphones in an array inside the car, then these microphones, using the specific techniques that we are going to talk today, they can grab the signal and do a kind of process over the signal in order to give a gain to that. And then it would be, for example, broadcasted using some speakers which are deployed to be, for example, next to the ears of the people, the passengers inside the car. Then the quality of the voice would be much better. And the same project is actually running, or was running actually, I'm not sure if it's finished or not, but by many companies. As far as I know, the Mercedes and BMW were trying to deploy such kind of system inside the car, and such that those people sitting as passengers behind, they don't need actually to shout in order to communicate with the driver, to say some statement to the driver, and the same way back. So that would be much easier inside the car. That's called in-car communication system, ICC. And we have a lot of other projects, similar projects. So we have also in seismology, normally we have, for example, you want to see how to see about the, for example, the reflections of some waves, that you generate those waves on the surface of the earth, and then you propagate these waves, and then the reflections of these waves come back. You want to actually to understand what are the layers based on those reflections. So you should have multiple sensors, and then these are some specific cases, but it can be generalized to many other applications. One of the most prevalent ones and the most useful ones in the case of medical application is about the hearing aids. So people that they're having actually the problems with hearing. There are some hearing aid systems, and they can use these hearing aid systems using multiple microphones deployed inside. Then they could easily localize those people talking to them, and using a gain, then they can have a more SNR in their in their inside hearing system, and they can understand the voices much better. And in case of the general array systems, we have this, for example, here you see these are the radar systems. These are fuzzy array radar systems. They are very precise. They can very precisely locate any source, even a very long distance, and many other things, many other projects. So here's a sample of a hearing aid system. Here is the one sample from this microphone array inside the car, and there are 4 microphones on top of the mirror, I think, and it can localize. If, for example, the speaker is the driver, it localizes to the driver, grabs the signal and gives the gain to the signal of the driver, and broadcasts the signal for the other passengers. And whoever's talking, the microphone array is actually grabbing the signal of that person specifically and sends to the other people by broadcasting. That's normally called the passive spatial filtering, but we have also some active spatial filtering. So we have it's called beamformers. So we have the passive beamformers and we have the active beamformers. The passive beamformers, they're just steering the beam of the array toward the speaker or the source. But we have a reverse system which can um, just broadcast the signal into a specific location. So we have also the same thing, and that also can have a lot of applications. As far as I remember, there was an application running a few years ago, and they were supposed to put a system inside a supermarket, large and huge supermarket like I don't know, Walmart, for example, and then there are shelves for different goods, so different varieties in goods that you want to buy, there are shelves for that. So instead of having people standing by those shelves and explaining about the quality of that those goods that you want to buy, so there would be a automatic system deployed somewhere inside this environment, and then whoever is getting close to one of these shelves, then the system automatically is actually sending a directed wave, by that wave explaining the quality of that the quality of that good that that person is going to buy, and explaining, advertising about that, and it's doing for every shelf that is inside that environment. And the same thing would happen for example, when an airplane or whatever like that is passing over, for example, an area, and in that area, for example, there is a military organization somewhere, and you don't want to pass the information which is so top secret to everywhere, to broadcast it to everywhere, and you just want to localize the wave, the broadcasting wave to the specific area which you already know that it belongs to the military service. So these are some of the applications that would employ the array processing and spatial filtering. Specifically for the case of acoustic source, if we come back to the human auditory system, so we know that we have 2 ears, and these 2 ears have the duty of gathering the acoustic information from the environment. But actually they're not doing that linearly. So what essentially happens is that when, for example, you're looking forward, then the gain of what you can actually understand this acoustic source is somehow can be represented by this nonlinear curve. So we can more understand what's in front and less understanding what's in the back. And it's not only for the case of so the front and back, but also we have this another pattern which works more for the case of elevation. So the elevation is also not linearly or uniformly actually scattered. So more elevation gain is actually dedicated for something quite in front and less for example, something on top. And that's why we have a set of techniques that they are actually using the head-related transfer function. So they are actually trying to investigate if you have this head with this specific geometry, then how should be the transfer function of the acoustic wave coming from different points inside the room and environment with respect to the position of the ears that we have and the scope of the people. So these are called the head-related transfer function, HRTF. They extract it out for some specific types of these calls, and then they can use it as a prior information in their acoustic signal, for example, localization or separation of the signals. Well, the position is not only the case, we have also the problem of frequency. So the more the frequency is, the more localized the source could be. So it means that when some people, they're talking, for example, when men are talking, because they are normally having some lower part of the spectrum is more activated, so the propagation of the wave is actually more broad and more people around can understand it. But when it comes to the, for example, children or the women, because the frequency of the women which are activated are more the higher part of the spectrum, then it's more localized in front, and probably people around will not be able to understand the from behind. And what really happens is that for the higher frequencies, a kind of shadow happens on the other side of the skull. So that's something that for the lower frequencies rarely happens, or at least we have a threshold for that. But for the higher frequencies, there's a shadow happening on the other side of the skull. So these are all the problems that occur for the case of human listening. And so these are two spatial cues, ITD and IID, which is the inter-ear time difference of arrival and level of intensity, the difference of arrival for the signal. And based on these all conditions, a combination of all of these cues, these geometrical and spatial cues, human is actually able to understand the position of the source and to actually grab the source, the wave or the information of the source. We have in industry, we also have different types of microphones. So it's not like that all the microphones are omnidirectional, so they can grab everything from all the directions. That's just one type of the microphone, and it's called omnidirectional. It means that this kind of microphones, they have the same gain for all the directions. Doesn't matter what from which direction the source is actually coming. But we have unidirectional, bidirectional, or semi-cardioic, and many other different types of microphones, and it depends on which microphone we are actually using. But for our case, specific theoretical case, we normally consider the microphones to be omnidirectional, and that's actually the worst case, for the process. Because if it's omnidirectional, so that would be the worst case to do the processing. One of the applications which is very nice for the array of microphones, is actually recording the noises or the sounds coming out of for example, a car engine, and then based on some real data you have already gathered from different cars, but not different models, then you would be able to understand if there is a car and it has some problems, then you would localize that component of the engine which actually creates that problem. And that's one of the methods that is actually running. I'm not sure if it's been already in the industry, deployed in the industry, or it's just in the research stage, but that's the idea is really nice. So let's go to the theory and to know what actually happens in the case of multiple sensors. Starting from the simplest case, where we have just two microphones and one source. So it's so easy to say that when we have two microphones, for example, if we assume that these two microphones are located on the y-axis and the vertical axis x with respect to that, then if there is a source S here, if the source is far enough, so we call that far field. So if the source is far enough, then the propagation of the wave from source to the microphones would be in such a way that one of the microphones grabs the signal faster than the other one, sooner than the other one. And it means that there would be a delay to grab this, the same information of the source by microphone M2 compared to the microphone M1. And we can easily calculate this delay based on the distance between these two microphones, which is D, this distance, and the angle of arrival. So assuming that the angle of arrival, if we assume that the origin is somewhere in between these two microphones and exactly in the middle, then if we assume that this angle of arrival is something theta, like theta, then it's easy to say that d times the sinus of the theta is actually this distance. And we know that, for example, the acoustic wave, if we are talking about the acoustic wave, like the speech case, so we know that the speech sound actually propagates in every in an environment, for example, like the room environment, with a speed like 340 meter per second. So if we know the speed of wave propagation and we know this distance, we can easily calculate the time. So the time difference of arrival between these two microphones would be d times the sinus of theta over the speed of sound. That's the time difference of arrival for these two microphones. And it depends on theta and the d, which is the distance between two microphones. Now let's go to a scenario which we're going to actually talk about how to...
So,
yes, please.
So d times sine theta, it gives us the distance or the time? Because
D times sine of theta is the distance, the difference. Let me explain it more clearly. This source propagates to this microphone and this microphone, but the source, in order to get to this microphone, needs to actually to be propagated and to spend more time, and this time is actually spent on a distance. What is this difference of the distance which the source is actually required to pass in order to actually be recorded by microphone M2? This is the part of the distance which is related to that, and this part is actually d times sinus of theta. And this difference in the so the longitude of the longitude which the source is going to actually pass through is something that makes the difference in the time of arrival. So the source is arrived in this microphone sooner than this microphone based on this much distance, which is the difference between the arrival for these two sources. Clear enough, huh? So we have this scenario, assuming that we are in a room. Well, that's the harshest scenario that we can imagine. So we are in a room. It means that we have a lot of reverberations, and we have a lot of noise sources. Not necessarily they are locational and point noises. It could be an ambient noise, which could be wherever. And for example, you have an array of microphones somewhere in the middle of the environment. And you have, for example, people as source, as speech sources which generate the speech, and we are going to locate these sources and grab this, the information of the speech that they are actually propagating inside the room. That's the scenario that we're talking. And there are a lot of other objects inside the room. We don't care about the objects, but the point is that these objects can create dispersion and reverberation and make the entire reverberation of the room something nonlinear and completely random. So it doesn't go further. Assuming that, for example, source 1 is talking, this man is talking, then the source is not just a direct propagation of the wave, but also whatever is propagated, it also hits the walls and the ceiling and the floor, everywhere, and then even passes through different objects and then comes back to the microphone. So whatever is recorded by the microphone is the combination of all of these direct source and the reflected sources. And the same thing for the second source, the direct one and the reflected versions. And it's not just one tap. You have millions of taps or thousands of taps, thousands of reflections that they are all gathered by the microphone. The first problem we're going to solve is localization of the sources. So how we can localize the sources using this array of microphones. First of all, there is a pre-assumption in this course in the array processing, and that pre-assumption is that we know about the geometry of these microphones in the array. So we know exactly how they are located with respect to each other, and also we know, for example, where we have put this array inside that environment which we are going to calculate our stuff. Okay, so we know that they are exactly, for example, in a circular array or it's a linear array, and the distance between every two single microphone, individual microphones is 5 centimeters, 10 centimeters, whatever. Or there's a radius array, for example, with the circular array with a radius of 20 centimeters or whatever, or a spherical array, whatever. But that geometry for us is known, and we're going to get information out of this entire, yes.
So we know the acoustics of the
We know,
environment as well.
the only thing that we know is just the array geometry. So we know the geometry of the array and the position of the array as a, for example, if you consider the center of the array to be in the middle in a circular case, we just know that this array is put in this location inside the room. That's all we know, nothing more than that. Okay, now sources are just randomly and wildly going through this room, and we're going to locate the sources, and afterwards we're going to actually grab the signal just from those sources that we desire. That's the problem we're going to solve. So the first problem is sound source localization, and sometimes if it's a single source they call it SSL, and if it's multiple sources it's abbreviated by MSL, multiple source localization. So these are the things that you may encounter in the literature. There are methods to localize the sources. One method is called the SRP method, which steered response power. So the SRP method, generally talking, it's actually using the power method. So it tries to actually to locate where inside this environment the array can actually observe a peak in the power. So we know that the source of generating an acoustic signal is creating a source, it can be actually considered as a source of power. So if we can see somewhere inside this room, somewhere from any position in the room that generates some power, it might be a source location. So that's the idea of the SRP or the SRP beamformer. The other techniques are based on the spectral estimation methods, and there are plethora of the methods in this category, like the Esprit method and music method, and these are actually using the spectral estimation methods. I'm not going to talk about these methods, and it's so simple, but it needs some background, and we're not going to talk about that, but it's just mentioned here if you want to go through that. So you can find the music, so MUSIC, but it stands for something, so it's not the music instruments or music playing, but that's a method. It's a very precise method for location finding, but they mostly work for the narrowband signals and not for the wideband signals. And you know that a speech signal is not a narrowband signal. Speech is a wideband signal. Even though the bandwidth is not too much, but with respect to its central frequency, it's considered to be a wideband signal. So they're not applicable in our case. And another series of methods which are called the TDOA estimation methods, or time difference of arrival estimation methods. So they're trying to estimate the time difference of arrival between every two microphones, and then based on that time difference they try actually to find out the location of the source. Okay,
depends on the
temperature.
temperature.
Mhm. So it's called the impedance of the air. So air impedance is something that depends on the density. So if you have, for example, something rather than air, when it's a gas, for example, a kind of gas, then it depends on the density of the gas and also the temperature. But in normal air, the condition which we have just air, and in a normal room with 22 degrees, which is called the lab conditions, is almost 342 or 43 meter per second. But then we have some other coefficients which you can easily calculate if the temperature is more or less, then how much the difference would be for the speed of sound. And it could be easily extracted from some tables, so it's not a problem at all. So TDOA based locators, they normally have two steps. In the first step, what we try to do is, so we have the geometry of the array. So what they try to do is, in TDOA estimation of sound between two spatially separated microphones, we calculate this, and then based on the geometry of the array, we try to map it to the 3D location of the source, which might be possible. But the point is that estimation of the time difference of arrival is so critical. If you make a mistake in that estimation, then the problem, you will definitely have some perplexity in the location of the source. In general, when you calculate these time difference of arrival, you need to calculate the cross-correlation function. You remember when we were talking about the random signals and the cross-correlation stuff? So we said that cross-correlation, if the signal is stationary, just depends on their time difference, on the lag. So if you do the cross-correlation between two signals and the signals are stationary, the stationarity condition imposes that if you calculate the cross-correlation, that cross-correlation only depends on their time difference, so or the lag between these two signals. So you have, for example, two microphones. They are both grabbing the same signal, but the signal is actually recorded with a time difference. If you make a cross-correlation, this cross-correlation as a function of tau, or the lag, it can be actually mapped into a hyperbolic curve like this. So all the points which are located here on this hyperbolic function, on the hyperbolic position function, they are the possible domain of these answers that can actually happen for the location of the source. So the place that maximizes the cross-correlation is the place of the location of the source. And that location is actually somewhere here on this hyperbolic. Mathematically speaking, if you calculate the cross-correlation function, which is something based on the tau because of stationarity condition, so it just depends on the tau. So you need to calculate the cross-correlation between signal x1 from microphone 1, for example, and a signal x2, and it's calculated and weighted by a weight psi, something that depends on y 1 and 2, and that's the weighting just in order to unify the cross-correlation response with respect to different frequencies. So we know that propagation for different frequencies are not the same. So with different frequencies, we have actually different types, different way of propagation. So that's why we actually use a weighting function in order to make it unified for all the frequencies. And there are different weight functions that could be assigned here, but the best weight function based on experimental stuff, empirically they have figured out that this weight function, at least so far, it works best. and it's called FAT, or phase-based actually weight function. So calculating the GCC function or cross correlation function and then giving the weight, which is called in general, and generalizing over the entire frequencies, that's called the GCC FAT, generalized cross correlation with FAT weighting. That's called the FAT weighting. So we know that, for example, if the source is located in the point P, is located, for example, in the point P, we know that the time difference of arrival is actually the difference in the distance which the source is actually going to be propagated divided by the speed of sound. But we know that in the vector base, if you consider the Cartesian vector based coordinates, then the vector, for example, with respect to the source to the microphone MI, the first, for example, microphone, that distance can be represented as the norm of P, which is the location of the source, minus MI, which is the location of the first ith microphone. For example, the first microphone. This difference is actually the distance between the source P to the microphone MI. And the next, for the distance between microphone MJ and the P as a source. And the difference between these two norms is actually representing that difference of the distance difference that the sound is actually getting to be propagated between these two microphones. So that's the time over the C, which is the speed of sound. It gives me the time difference of arrival for microphone 1 and 2, or I and J in general. So that's the time difference of arrival as a function which depends on P, location of the source. After calculating this cross correlation function, which depends on tau, and tau is this way depends on P, then the tau as an argument which maximizes the cross correlation is the tau that we are looking for. And when we get the tau as the maximizer of this cross correlation function, you have the tau, you put it here, you have the C, you have the position of the MI and MJ, and you can calculate the P as a position of the source. Okay? So that's the way how GCC FAT, by having this weight function, FAT function, weighting function, we are actually locating the source in that environment. Okay? So that was the method of GCC FAT. So what's the difference between the SRP and GCC? So the SRP says that because GCC function, in general, if your environment is so reverberated, you can get a lot of peaks. So it's not just a single peak that you can get. You might get a lot of peaks. And then you will face with some problem, which of these peaks you have to actually pick as the real peak, which denotes the source location. SRP in general, what it does is that considering this Q to somehow denote for the pairs of the microphones. So if you have an array using an array of, for example, M microphones, then you have Q number of the pairs of these microphones that you can have. And for example, if you have M, then M times M minus 1 over 2 is the number of the pairs that you can have. Between every two microphones you can have is considered a one pair. Then how many pairs you can have is 2 from M. As a 2 choices out of M. So it's M times M minus 1 over 2. So the capital Q is actually M times M minus 1 over 2. These are the number of the pairs that you can have. And for each pair, you calculate the cross correlation function. Then, so you have the cross correlation function for each pair, and there's one source located in the place P. After doing that, you take the average. So you're averaging over the cross correlation function of what we got from all the pairs. That's the SRP function with respect to the free variable, which is P. And what we do then is finding the P, or the position which maximizes this SRP function. So intuitively, SRP works like that, looks for the maximum energy inside the room. So greedily, it actually looks for the, the energy points inside the room, because the cross correlation is actually a function which represents the variance, and variance is energy. So if you're looking for the maximum variance, you're looking for maximum energy. So inside the room, assuming that this room is granularly, separated into different grids, then it tries to look for all the grids and to grab all these, so the places which the generalized cross correlation, taking the average in that place, gives the maximum energy. Okay? And that's the SRP method. So we talked about GCC and SRP, but there are another methods, as I explained, a spectral estimation based method like music, Esprit, and similar methods. So whenever you want to do something fast, it's better to do TDOA based methods, so the GCC function, even though there are ambiguities in it, but it's fast enough, so you can implement it in real-time case. SRP method is more precise, and you can get more accurate solutions out of that. But the point is that because it's a greedy algorithm and it looks for every single center inside the room in that grid, then it's greedy, and it might take a while, and then computationally it's not that much efficient, and it might take a while. So it depends on your processor, but TDOA based methods is always faster. And if the precision is important for you, so it's better to go to the SRP method. One point is that when we're looking for the source should be active. If the source is not active, if he's not talking, even if he's existed in the environment. So for example, assuming a case that someone is talking, but he's silent for a while, and then he again starts talking. For that period of time in which he's silent, so what you will do with the location of the source, what happens to that? So the point is that we have to consider another functional block diagram here, which is actually the voice activity detector. So we go for the source localization algorithm whenever the voice activity detector indicates that there is a source here in the environment. There is a source which is active. So the entire process is happening like this. So we have the array of microphones here. We get this information from the array, then calculate the voice activity detector, whether there is a source or not. And if it's active, or the probability of this hypothesis, which is the activation of the source, if this probability is high enough, then we trigger the one frame, for example, single source localization method. And then for that case, for example, the SRP method is running. And the output of the SRP and then is actually passed through a processor after doing the calculations to map it to the 3D dimension and then getting out the environmental position of the source. But the point is that this is, for example, for tracking algorithm. For tracking algorithm, it means that the source is not stationary. So there is a person inside the room, but that person is not stationarily sitting somewhere or just standing somewhere. He might, decide to change his place. By doing that, and also in the middle, he's going to be silent for a while. What we have to do is we have to run a voice activity detector to just grab the source location and those frames which we are certain that he's active. Let's talk about beamforming and blind source separation and the difference. So whatever we talked so far is applicable in the case of beamforming. In the beamforming, which by default we considered a geometry for the array of microphones, and then using those GCC based method or the SRP based method, we could direct the array to the source which we desire. In the case of blind source separation, we have no geometry considered for the array, even though there might be some geometry for that, but we don't know that. There is no information of the array geometry. The only thing we have is some recorded signals out of those microphones. That's all. And for the blind source separation, we are actually looking for a method in such a way that we can extract the signals corresponding to each of these speakers just based on the signals recorded by the microphones. So the enumeration of these signals, the recorded signals, should somehow, using this BSS method block, should be actually giving us a gain in such a way that we can extract the sources. We will talk about BSS in the next coming lecture, so that's why I'm not going to talk about this. That was just mentioning the difference. So what beamforming does? Beamforming is a system that if you know the location of a source, so if you know using the GCC method or the SRP method that there is a source somewhere in this location, then beamforming is actually a method for spatial filtering. What does it mean? It means that filter the entire space in such a way that only signals coming from this direction be given a high gain, and for all the signals coming from any other directions, we try to null that signal. Okay? So, giving the highest possible gain to the desired direction and nullifying all the signals coming from any direction other than the one that we desire. That's called the beamforming system of the beamforming. One of the simplest ideas that come after definition of the beamformer is that, for example, if we have some noise sources or interference sources and we have a source of desired the desired source, then based on the idea of wave propagation, if we can, for example, for that desired source or the target, if we can align the signals of the microphones based on the time difference of arrival, then they are, after the signal alignment, they are synchronized, and then if you sum them up, definitely the signal in the output would be, as a result, would be a gained version of the signal, these aligned signals. So you're summing up, because it's a synchronous signal, so you're summing up the signals, and whatever you get in the output would be definitely having the more gain than the signals individually. And for the noise sources, because you don't do the alignment, then probably they would cancel each other in many places, or at least we're sure that the gain would not be comparable to the one that we have with synchronous case, the time aligned version. So that's the idea of delay and sum beamformer. The very first and beginning version of the beamformers, which is applicable in many areas, from the acoustic area to the antenna and so on, is delay and sum beamformer, abbreviated by DSB. So the idea is that, so in the vector form, this time difference of arrival in the vector form can be represented by MI, which is the real position of the signal, the microphone, position of the microphone, times A, which is actually the array, is called array manifold vector or array propagation vector. So the inner product between these two is actually showing the distance, the difference of the distances that the wave propagates, and over the speed of sound, it actually gives you the time difference of arrival. So that's just the vector form of representing what we already explained by the norm. And this A is actually just this, this form of radial form of representing this, the signal which is propagated. It's so simple. Just look at the figure, you can get it out.
What is phi? Theta is the angle of the source, and phi.
Theta is the azimuth, and phi here is called as the elevation. But it's it depends. In many literature, maybe they are substituted. One is called as the azimuth, the other one is elevation. So, but in this case, it's just this way. So, if you line up a vector, which is called the V, or the array manifold vector, and which actually represents the time shifts. So we know that time shift shifting in the time domain is actually corresponding to the e to the power of j omega or j phi in the frequency domain. So if you try to line up everything, the phase shifts between the wave propagation for each of the microphones with respect to the source, if you line them up in a vector but in the frequency domain, it would be the vector with the elements has to be e to the power of j and the phase shifts. So we can assign the first microphone to be the origin, then you can put this one to be 1, and the others for the rest of the microphones would be with respect to the first one. So it can also be lined up like that, but it's not a big difference. So you can just assume these are the phase shifts. J omega tau 1, tau 2, until how many number of the microphones you have here. So these are representing the phase shifts. Then the signal in the microphone can be actually shown as the source propagated by this array manifold vector plus some noise. So there's one statement dropped here. I had to write it down. That is x equals to SV plus noise. That's the only thing dropped here. And the goal of the beamformer is to apply weights to these microphone signals in such a way that, if you can assume that this is the weight for every frequency, we're talking about every frequency. So in such a way that by applying these weights to the signals of the microphones, so W is a vector containing W1 corresponding to X1 here, W2 for the X2 and WL for XL. So when you line them up in a vector W, then applying these weights to these signals of the microphones to get the signal of the desired signal and cancel the noise as much as possible. That's the goal of the delay and sum beamforming. But for the delay and sound beamforming, as I explained in the previous slide, we're just going to simply line them up and just taking the average. That's all. So here, simply by choosing W to be the same as array manifold vector, or the propagation vector actually, if you choose W to be like that, when you do the W Hermitian, it makes the conjugate, and conjugate, it means that every negative here should be positive, and so you are compensating all the phase shifts, and by doing that you're actually aligning all the signals for all the microphones. And so W Hermitian times V here, because S is considered just single source, so it can be taken out. You just apply this vector to the vector V. So W Hermitian V means aligning all the signals for every single microphone. And by this alignment, you're compensating for all the phase shifts. And then times S, it means that you sum all them up. And then by 1 over n, you're taking the average. So you take the average after time alignment, the same as what we explained here. You take the average after time alignment, and that's the signal in the output. But this W as a weight is also applied for the noise, and we hope for this part, the second part which belongs to the noise, to be attenuated. So that's the idea of delay and sound beamformer. At least we are sure that the signal is having a gain now. You're summing up the signals at each microphone after doing the alignment. So that's why the signal definitely is having some gain based on the number of the microphones that you have. With respect to the noise, which we are sure that the noise is somehow cancelled, not completely, but it's attenuated. Why? Because noise is a random source. So it doesn't make sense to have W chosen in such a way that by doing some phase shifts in the microphone, the noise part of that, when you're summing them up, to be magnified, because it's a random source, so probably it's not magnified. Any questions?
Sorry, why is the formula x omega equals to s times b plus n?
Maybe let me write it down here. In general, if you have these microphones, for example, M1, M2 up to MM, microphone 1 up to microphone M, and you have a source S here. Source is propagated for every single microphone, and there is a difference. For example, if assuming that this is the closest one and this is the array direction, then the source arrives to the microphone M1 sooner than any other microphone, but there is a slight difference here, then a bigger difference here, a bigger difference here, and the maximum difference here. Okay? And here you have D, you have B, and so on. So multiple Ds. Assuming that it's far enough. Now the point is that source is propagated. It means that source is passed through a filter, the propagation filter, and then is grabbed by a number of microphones. That propagation filter is called room impulse response. So that's a filter. Source passing through the filter of the room, and then being recorded by the microphones. Okay? This array manifold vector says that x, which you are recording, here x means x1 to xm, x that you are recording in the microphones, each of the microphones, is actually a filtered version of S by convolution. So here's a vector as a filter, assuming that this is an FIR filter. Okay? In general, it's not FIR, it's IIR, because there is no real filter to be FIR. It's normally an IIR. For example, H is an, I don't know, whatever, 0, 1, minus 1, half, and so on. So you can assume that this is an FIR filter times S, the single source signal, plus some noise. And this noise, for each microphone you have some noise recorded. Now take it to the Fourier domain. In the Fourier domain, you have x, here you have everything based on time. In Fourier domain, you would have x of omega. This convolution changes to times s, and this is a scalar, just the source in the omega, plus the noise. Okay? So x is hs plus noise. Now the point is that in delay ensemble beamformers, or in general in the beamformer cases that we explain actually, they assume that this propagation is simply a function of the phase shifts. So that propagation is actually represented by this v vector, which is dependent on w and is represented by e minus j omega, for example, 2 and minus j omega tau 2 and tau n. Assuming we can normalize this vector, so that the vector is normalized in such a way that assuming there is no shift for the first one, there is tau 2 shift for the second one, tau m shift for the mth one, the final microphone here. So that's called array manifold vector, array propagation vector. So the source is propagated by this filter and then adding some noise recorded in the microphones. Okay? So x is equal to dropping the dependency on the frequency. X is equal to Vs plus noise. The goal of the beamformer is to find a W such that when we apply the W on X, we can get the signal. Okay? Applying W on X is a filtering. You're doing a filtering. So X should be filtered such a way that we get the signal. Completely reverse order of what we had here. So here you have sine mode system, single input, multiple output system. You have here MISO system. Multiple input, single output. Okay, so W as a filter should be applied here. In the frequency domain, filtering is multiplication. So, or let us just write down W Hermitian, because in complex case you have normally the W Hermitian. W Hermitian X, it should be approximated as the source. That's what we desire. We have to apply W in such a way that we have to grab the source, to get the source back. But it's just an approximation. What really happens is that this equals to W Hermitian Vs plus W Hermitian noise. That's what really happens. Okay? We hope that these two cancel each other, and this is also attenuated. Attenuation of this and cancellation of this is our hope. The simple idea of delay and sum beamformer is to choose W to be 1 over n V. Then W Hermitian is 1 over n V Hermitian. And Hermitian of this is just changing the sign of all of them as plus. Okay? Now, if you apply this, these two will cancel each other. Because one of them has positive signs, one of them negative signs, you sum them up, they become so the Hermitian is conjugate and transpose both at the same time, so that's why it becomes 1 e to the power of plus j omega tau 1 or tau 2 e to the power of plus j omega tau 3 and so on times v, which is v plus v that's the approximation. Okay, now do this calculation. 1 times 1, this times this, this times this, n times n. So n over n, that becomes 1. 1 times s, so W Hermitian x gives us s plus the value here. So we've got s, but we also have some part of the noise, and we hope that this is attenuated. Normally it's attenuated. Why? Because n is noise. It's a random, fully random Gaussian noise with mean 0 and some variance. Okay? Because you're summing up after doing the alignment, just you're doing the alignment in the signal in the microphone, and then you're summing up. It's random. So rarely happens that for a random signal, when you do the time alignment in different microphones, by doing the time alignment, you're increasing the weight, increasing this amplitude of the signal. Rarely happens. Because it rarely happens, even if so the maximum, the worst case is that it's also synchronized, so it's actually completely synchronized, and then the gain would be increased, and by increasing the same gain, so the source and the noise, they are both having the same gain, so the SNR is not changed. That's the worst possible case. But normally it's not the case, because it's fully random. When you time align this one, then it's not actually, it's somehow mitigated, but this one is, having a gain, and then the signal to noise ratio is improved a lot. That's the idea of delay and sum beamformer. I didn't want to go through that, but maybe it was better to write it down, and it's easy, you can understand. So by doing that, maybe I can add one slide next, afterwards. I have already uploaded it, but maybe I will add one slide to write down all these calculations also. So that was the idea of simple delay and sum beamformer, just to time align everything and then take the average. By doing that, you have a gain. Signal to noise ratio will be enhanced. But we have optimization based beamformers, And for the optimization-based beamformer, we're trying to locate the signal, or to have the, directing the array toward the desired signal, this desired source, to have the maximum possible gain, to have the maximum SNR, or maximum possible gain. So there is a big difference between the result of what we get from delay and sum and, for example, very famous method of SuperDirective beamformer as an optimization-based beamformer. So here you see the pattern, gain patterns for different frequencies. So here it's for 20, how much is that? I cannot read it. 250 hertz and 500 hertz, 1 kilohertz and 2 kilohertz. So we see that for different frequencies, the pattern, the gain pattern is different. For SuperDirective beamformer, you see that the pattern is more robust, and for different frequencies, you have a good direction for all the cases. And the direction is much tighter of what you have for the delay and sum beamformer. So delay and sum beamformer, or just simply this averaging, delay and sum beamformer doesn't really work well for low frequencies. It seems that for low frequencies, it's grabbing the signal from all directions. So it means a lot of noise and a lot of reverberation would be inside. It's just like you have never manipulated the microphone signals. So you are just listening to the crude signal recorded by the microphone. You have no gain. But for the higher frequencies, you will have a good gain, completely improved. But when we go through the optimization-based beamformers, then the SuperDirective beamformer as an example, then you have a good gain for all the frequencies. And it's completely directed. So you see the signal, for example, assuming that the source is from this degree, 90 degrees actually talking, we can direct the signal and steer actually the array microphone toward the signal of the desired signal and target, and grab the signal just from this location and to nullify all the signals coming from any other direction. So you see that the pattern gain is just toward this direction and has been nullified, zeroed for all the other directions. So that would be a lot of gain here, while you don't have that much gain here for at least for the lower frequencies. So that's the place that one of those things we talked about in the optimization case appears actually. So we are trying to find, so you see that here we are applying W to as a filter to the X. So this way of applying filter to the signal of the microphone is just a linear application. So it's linear based on so we are applying this function. So the output, or the S estimate, we are actually saying by this statement, we are saying that S estimate is actually W Hermitian times X. And I write down Hermitian because we are in the complex domain. Everything in the Fourier is complex. That's why I normally write down as Hermitian. If it was real, I easily could write it down as transpose. When it's complex, the conjugate transpose is called Hermitian. Okay? So we have the S estimate, estimation of the signal, to be the W Hermitian X, just like filtering X by W. Okay? And that's a linear estimation, because S as an estimator is just a linear function of X, so you are doing a linear estimate. Clear so far? Okay. Let me give you some time to write down everything we need. So finished? Okay, so let's go back to the optimization. So we have a linear estimate. A linear estimate. We have the xt. Let's go through this linear estimation. You already know about blue. I said best linear unbiased estimator. You remember that? If we have an estimator which is linear based on the parameter, it's called linear estimator. Then we talked about something as MVUE, maximum variance unbiased estimator. Then we said that that's not possible. We go to the linear case. The best linear unbiased estimator is called blue. And the result of this optimization problem is called the MVDR beamformer, maximum variance distortionless response beamformer. And this is the way how it's calculated. The complete calculation I have actually put it in the slides, and I'm not sure if you go to the internet you can find actually the complete calculation anywhere. So you have it in the slides. So I'm not sure, I'm not claiming that 100% you'll not find it, but at least I have, I've not found it. So these are mostly gathering from all the other, all the articles and then putting them together to have something solid as a solution for the MVDR. Xt equals to, as I explained here, it equals to this filtering or room impulse response convolved by the signal or the source, and then having an additive noise. And I generalize that for multiple sources. So if you have multiple sources, you have this matrix. Otherwise, you have just a single source. You have just single vector. And these are the dimensions. So x equals to Vs plus noise. Now the point is that we need to have an estimator, which is a linear estimator having this parameter x. And as a linear estimator, we are going to actually apply this W. So the best linear unbiased estimator should be unbiased with the minimum variance. Let's investigate the first property, which is unbiasedness. Unbiasedness means that the expectation of the estimate should be the expectation of the true value. Now replace the estimate with the one we have in the filter. So it means that this should actually hold. And then by replacing x with the one we have here, we will get W Hermitian V, expectation of true estimate, true system, true signal actually, to be expectation, and this will vanish from both sides. So that's the constraint, that W Hermitian V should be 1. The same thing that we got here in delay and sum beamformer. Remember? Delay and sum beamformer had this constraint. So we actually, this first one is something that we already got from the delay and sum beamformer intuitively. It's so simple and intuitively we could get it. But it's not all. In delay and sum beamformer, we never try to minimize the variance, but here we go to minimize the variance. Now calculate the variance of estimate. The variance of estimate would be this term. So just replace the estimate S by replacing this with the W Hermitian X and subtracting the mean of that, and then expanding the X with the one we have as the expansion, Vs plus noise. The only random parameter is X. W could be taken out of this expectation. So it becomes W Hermitian times the covariance matrix of signal X times W. That's the variance of estimate. And just remember that when we have W Hermitian X, so the variance would be W Hermitian covariance of X times W. Okay? Now the optimization problem becomes, the face of the problem is here. find the W which minimizes this variance subject to this constraint. Okay? Now there is a point that makes things actually simpler. Assuming that, so we know that the signal and noise are independent. When they are independent, the correlation between signal and noise would be 0. That's the condition of independence. And the other way, noise and signal or signal and noise, they are orthogonal. So the correlation would be 0. Replacing x with its expansion and then applying the Rxx instead, we get this value. But we know that the only part which is related to, so apply this, this is Rxx, and then in the previous slide we had W Hermitian Rxx plus times W. So if you apply W Hermitian and W from both sides, then you have W Hermitian V RSS V Hermitian W plus the next term. But this W Hermitian V from the constraint is supposed to be 1. And also from the other side is also the Hermitian of 1, so it's a scalar, it should be again 1. So it means that by applying this, the constraint, the face of the problem, W Hermitian Rxxw becomes RSS plus this term. And this first term is actually doesn't depending on W at all. So minimizing the term, the complete term, is just minimizing this term. We replace that and the problem changes to W Hermitian covariance of the noise W subject to the condition that we have, the constraint that we have. So instead of going to the X, we are not trying to actually minimize the variance of the noise in the microphones subject to the constraint. Now the problem becomes a bit simpler. Even it's becoming more simple. Why? Because we have some conditions on the noise. So there are some properties of the noise in the environment that we can employ right now, and we can find a better solution for that. So what we found actually here so far is the MVDR beamformer. So without conditioning the noise, if you have no prior information about the covariance of the noise and you apply just the noise covariance matrix here, you are calculating the MVDR beamformer. But there is something happening in reality, and this really helps. And if you apply that prior to that MVDR problem, optimization problem, you will get SuperDirective beamformer. And that's the prior information that you have. In the room environment, normally you have isotropic noise fields. Isotropic noise fields or homogeneous noise field. It means that the power of the noise at every location of this array of microphones, they have the same power. Or it's isotropic, it means that from each direction you're actually having the same pattern of the noise, the same noise power. So it means that this covariance of the noise is actually a constant, which is a noise power times the noise coherence matrix. And this noise coherence matrix, let's extract this, derive this noise coherence matrix. So homogeneity or isotropic property means that the spectral density, the power spectrum at microphone MI and MJ, they are equal. That's the condition of being isotropic. So the noise power spectrum at microphone MI is the same as noise power spectrum S at microphone MJ. And the cross power spectrum just depends on their delay of arrival. So the cross power spectrum between microphone I and J is just one of them, which is SI, and the phase shift difference between these two, which I already written here. So we have xj, for example, xi shifted by time delta over c, and delta is the time difference, the distance difference, which is the cosine of phi, for example, here. And the time is delta over c, which is the speed of sound. So that's how we represent this. Now the spatial coherence is actually the integration over the entire area that these two microphones you have for the cross power spectrum normalized by their specific spectrum, power spectrums. Applying this, because we have the spheric isotropic property, then you can apply the dA, and we know that A is a sphere with 4πr square, and the phi and theta are the angles changing in this range, getting their value from these ranges, 0 to pi and 0 to 2 pi, and apply this here. Then you see that this coherence, the spatial coherence between microphone I and microphone J with respect to the omega, the frequency, is a sinc function. The sinc function which only depends on the distance. C is a constant, the speed of sound, and the frequency, and here you have a sinc function. And this D, you know that is the difference between microphone MI and MJ over the, yeah, that's D actually. So, this covariance matrix of the noise, which is the noise power times the coherence matrix of the noise, you can replace this coherence matrix with this, which the elements are extracted from what we wrote here, or again remember here. So the sinc function like this between every I and J microphone, and you can write it down for all the microphones, the pairs of the microphones, 1 to M and 1 to M, and every two pairs you have this sinc function here. So replacing that, because it's a noise power which is constant in every environment, the SuperDirective beamformer is the optimization problem, the same as MVDR, but you're going to actually apply this W, minimize based on this W, and this means that you don't need actually to look for this phi of n. You just minimize W Hermitian, coherence matrix of the noise, times W subject to the constraint. We simplified everything. And it's interesting that this part is only dependent on frequency. It doesn't depend on anything else. So the frequency, MI and MJ, the position of the sources, and so on. Now you have this problem to be solved, and you get the result. If you do the Lagrange multiplier, the SuperDirective beamformer will actually come up like this. So you just calculate this offline method. In an offline, you can offline just calculate this matrix. Coherence matrix can be calculated in an offline process. When you calculate this, if you have the position, this V can be calculated so simply, and then the same thing here goes here times V. The same thing here is here actually. Then you just apply V Hermitian to that, and you have the gain for the SuperDirective beamformer. Implicitly means that if you know the direction of the source, you can calculate the SuperDirective beamformer weights in an offline process without going to the process. You have the weights before you start your process. And you can simply apply and get the gain. So SuperDirective beamformer is actually the best blue beamformer in isotropic noise field. And that was only because we have an isotropic noise field. The only thing that helped us actually to get to that. And that Lagrange multiplier, I have done the calculation, but it's just for your knowledge. So we apply the Lagrange multiplier, doesn't matter whether to be plus or minus. Then you take the gradient with respect to W and with respect to the lambda. For the first case, you get the W as this, and then for the second case, you have this. You get the lambda, put it in the first one, and you get the W. Okay? So, there is another type of beamformer which is called the LCMV beamformer, linear constraint minimum variance beamformer. And with this beamformer, if you have multiple sources, then you can generalize the idea of SuperDirective. So here you see that here this solution is exactly the same as what we had here. So this W, just look at this one, and instead of 1 over this term, make it as inverse. So this term and this one inverse. Then you see that this term inverse is just the denominator. But it's the generalized version of a SuperDirective beamformer. When we have two sources, then you do the generalization. You have two sources, therefore you have V1 and V2. But then you can give, you can get the weights in such a way that for the first one you have 1, 0. For the second one you have 0 and 1. And you get the LCMV beamformer in such a way that puts a null. It actually calculates the weight in such a way that you have all the gain toward the desired beamformer, while you know that the second source is also locating somewhere else, and you put a null exactly in that place. So you force that you put a null in that place, and the other way around. When you're looking at the other one, so you're actually getting the source from this one and putting the null in the direction of the other one. So that's the way that LCMV beamformer works. Okay? So we are going to the final slide actually. Remember that whatever I talked about today was about the constant beamformers, fixed beamformers. We have adaptive beamformer that I didn't talk about that. Adaptive beamformer like this. So we have the LCMV beamformer in adaptive case. We have generalized cross correlation method. I'm not sure if in the afternoon I'm going to talk about that or not. If it's enough for you, I will not go through that. If you think that you need to spend something like 10 minutes more and learn something more, I will explain about that. That's not a problem for me. It depends on you. But otherwise, we'll go through some MATLAB examples from this SuperDirective and delay ensemble beamformer to see the patterns and how it is getting the gains and so on. So the room impulse response, things that we explained already about the room impulse response, and I said that it's actually an IIR filter, it's not an FIR filter, actually looks like this. So you have, for example, the source is propagated to the microphone. So the first tap is actually the direct sound. After some delay, it's actually grabbed by the microphone, recorded by the microphone. Then you have some early reflections, the very beginning reflections, coming very sparsely after the direct one. But then afterwards, these reflections actually become very dense. So thousands of reflections then come, all at the same time. So the next part, which is the late reflections, they become actually so dense. Only the early reflections are so sparse, but for the rest, after some time, it becomes so dense. And this time is actually between 50 to 100 milliseconds. So only the 50 up to 100 milliseconds of the signal are the direct and the early reflection part, and the rest belong to the late reflection. It's interesting to know that early reflection part of the impulse response actually helps to understand the speech better. So it's much better to have early reflection than to have a dry source, just having a direct signal. But late reflection corrupts the signal and deteriorates the way we can understand the signal. So the intelligibility of the speech with the early reflections is actually enhanced, but late reflection deteriorates the intelligibility of speech. So they say that early reflection colors the signal, make the signal colorful and beautiful, so people can easier understand this speech. But for the late reflection is actually getting troublesome, so people are annoyed and they're intelligent. I mean, they cannot understand and discern the words actually. That was the entire thing we talked about, so the geometry array and directivity and the location of the sources, and then constant beamformers that we talked about, which were also called the spatial aliasing. And if you have any questions, I would be happy to get the questions.